Good morning, sir. Hello.
Hello, hello. Yes, good morning, Harsh.
Good morning, sir.
I think I should not wish good morning to you. It's night over there.
Yeah.
All of you, good morning. Attendees, good morning.
Good morning, sir.
Good morning,
Good
sir.
morning. Good morning. Good morning.
Good morning, sir.
Okay. So we
Morning,
wait
sir.
for one. We wait for 1-2 minutes, and we start. Okay, it's 10 to now. We wait for 2 minutes more. Is it okay, Harsh?
Yeah, that's fine.
Okay. Okay. So shall we start, Harsh?
Yes. Yeah, we can start.
Okay.
Hello.
Yeah. Is it audible?
Yeah, I
Hello.
think
Yes, sir.
uh hello.
Is it audible to you, Harsh?
Yes, yes, it's audible now. Yeah. I think I
Okay.
lost you in between. Yeah.
Yes, sir.
Okay. 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 No issue. No issue. So it's my pleasure to introduce our alumni, Harsh Acharya. He was the student of 13th batch Automobile Engineering Department and graduated in 2017. During his graduation tenure, he has achieved class topper position. To achieve the future endeavors, he has joined Master of Science in Automobile System at Michigan at University of Michigan, USA in 2019. After his master education, he got placed at Ford Motor Company as a system validation engineer. And since in 2019 to till date, he is serving with automotive giant Ford Motor with same designation, system validation engineer. And today he is with us to interact his juniors, to interact the all automotive engineers. Some are going to be engineer in few days. Some are in the third year, second year. So it's a great moment for all the automotive engineering student, ADIT automobile engineering student, to interact with your junior, your senior, and he will give you the what kind of revolution already taken place worldwide as a automotive systems. So without wasting much time, I'll hand over the session to the Harsh Acharya. Harsh, it's over to you.
Yeah. Thank you very much, sir, for the introduction. So, yeah, without further ado, I'll get started. Hello, everyone. Good morning. Thanks for taking the time to join this seminar, and I hope after this talk, maybe I'll maybe I might be helpful in igniting some of the thoughts and future endeavors that you guys would be taking ahead. So let's start. I'll just turn off my video and I'll share my screen. Am I audible?
Yes, sir.
Yes, sir.
Okay. Okay. So today we have gathered here to talk about model-based development. So before we jump into the topic, I'll be discussing about I'll be giving some background why I chose this topic and why it's important. And once we go ahead, we'll also discuss some examples, and I'll also work through some of the models that I worked myself during my master's over here. So I think a bit about myself. I think Kuldip sir already gave a good introduction, so I'll skip this part. So here, here is a slide of vehicle network architecture. So basically, although the automobile, the modern day automobile, is primarily a mechanical machine. So all the majority of the components are mechanical. However, for their control and for their operation, there has to be a electronic control unit which is controlling all of these mechanical components. So let's say engine or the transmission unit or even our doors, our windows, our seats, our climate controls, our radio and infotainment systems, everything is being controlled by an ECU in the back end. And all of these ECUs need a huge amount of software to be embedded into the circuitry to attain the entire functionality of the automobile. So as we can see on the screen, uh, as we can see on the screen, these are some of the ECUs that we can see in this layout. And all of these ECUs would be communicating with each other. So an ECU cannot function itself as a standalone unit. They all work in harmony with each other, and they all are connected via CAN communication protocol. So this is the lifeline of a vehicle. Almost all the vehicles built in past 20 years, I would say, and all of these ECUs communicate with each other via CAN. And in within CAN, we have several classifications of high speed CAN, low speed CAN, based on the baud rate that is set for those harnesses or for those CAN networks. So we won't be discussing much about CAN networks today. We will just be discussing about individual ECU development. So here is a even further breakdown of majority of the ECUs that we find in a vehicle today. So the engine control unit, as the name suggests, is the control unit that controls the engine. So when I say controls the engine, although the main input is coming from the driver, from his accelerator pedal, but all the other inputs, as how much amount of fuel uh, do we need to let in the engine, what is the amount of oxygen that is being sensed at the exhaust, and all the other type of parameters are being controlled by this ECU, engine ECU. These are some other examples of the ECUs present in the vehicle. So now this, if we talk about restraint control ECU, what that means is basically airbags. The airbags that are there in the vehicle, they would need to be deployed by a control unit. So this restraint control unit would be dependent on lot of sensors that would be situated in the front end and the back end of the vehicle, which would be detecting a crash. In case of a crash, those sensors will be detecting a certain amount of force, and if that force has crossed the threshold, once those forces are uh, sensed, they will send the signal to this restraint control ECU through the CAN network that we just discussed. and the restraint control module will in turn deploy the airbags. So this entire process would be taking place in a split second, but it all has been possible because of all these ECUs. So today we'll be talking about how the actual software that is integrated into the ECU is developed. And this particular process that we are talking about, model-based development, is not specific to any ECUs. It is being used in development of all the ECUs that we are seeing on the screen right now. So almost entirely all the ECUs that we see in the vehicle are developed with model-based development. So as we discussed, the modern day vehicle has up to 80 electronic control units within themselves, and that is why this has been like utmost utmost importance in any vehicle development cycle. And model-based development is something that has been used since past 10 years, I would say, in almost all the automotive companies around the world. So uh, some of the advantages that MBD gives us is very quick development cycle, decreased cost, and improved performance, and more control of the features and more control of the mechanical components. So when I say improved performance and improved coverage, what kind of flexibility it gives the manufacturers is, if we give an example, the engine control unit, the amount of code and the complexity and the sophistication of the code that is present in the ECU sometimes allows the engine manufacturers or the OEMs to use the same engine for variety of purposes. So let's say that a 2-liter engine is being used by a company and they are just making changes in the calibration parameters or in the software that is controlling that engine, and with the help of that they can use the engine in n number of applications. The engine's power can be varied from, let's say, 150 horsepower to 250 horsepower. They can lock the power that they want the engine to max out at based on the software. So the same engine they can provide in a compact sedan also, and they can also provide the same engine in a full size SUV. So all this is possible because how we are developing the software that is going to control the engine, and and uh, the embedded system behind it. So now these ECUs, apart from working in harmony with all the other ECUs, they also need an input and output mechanism along with it. So when I say input, there are n number of sensors present in a vehicle. So all these sensors give work as an input parameters to all the ECUs. So it is not specific that one sensor would be just giving an input to one ECU. It would be giving input to n multiple ECUs. And similarly, ECUs, after receiving that input and based on their control logic, give out an output. And based on these outputs, all the actuators are controlled in a vehicle. So if we go over these sensors, I've listed some of the examples of sensors that are used in almost all the automobile. So temperature sensors, they basically temperature sensors are used a lot in the vehicles. They are used to sense the engine temperature, exhaust temperature, intake air temperature, the cabin temperature of the vehicle, the outside air temperature. So these are some of the applications of the temperature sensors. Position sensors, speed sensors. Speed sensors would be used to measure the engine speed, the wheel speed. So the speed sensors would work as an input for the ABS module, for the engine control unit, for the transmission control unit. The humidity sensor, which is present inside the cabin, will be working as an input to the AC compressor. The sunlight sensor did not used to be incorporated in olden day vehicles, but since now we have all the auto headlights, auto brightness and dimming level of the cluster and the dashboard, the sunlight sensor is used to increase the intensity and decrease the intensity of the headlight as per the sunlight intensity. And radar and lidars are the newest form of sensors that are being used in the present day automobile, with applications ranging from advanced driver assistance system like adaptive cruise control, lane keeping assist, lane departure warning, and even le- uh, all the levels of autonomous driving. And proximity sensors are used in park assist, active park assist, and rear cross traffic alert. So these are some of the sensors that work as an input to the ECU. And actuators is what are controlled by the ECUs and which help us close the loop, basically close the control loop. So when I say actuators, so if we take an example of the windows in our car, so we have what we call power windows, which are automated. With the press of a button, we can pull up the windows or pull down the windows. So that is controlled by a motor. So motor, in technical terms, we term it as an actuator. When we select that we want the airflow coming out of the front panel vents or the front defroster vents. So all this airflow is also controlled by the motors. So these are all examples of actuators that are controlled by these ECUs. Solenoids, which control the solenoid valves used in engines, in exhaust, are also a type of actuators which is controlled by the particular ECU. And we also have hydraulic and pneumatic valves which are being used in braking systems. So now coming to the main topic, what is MBD? So model-based development is basically a software development methodology which is based on the V cycle of the software development process. So V cycle will come to that point, but V cycle is basically a software development cycle which was developed to provide a testing of a system while it's being developed. Earlier, what used to happen? Someone is developing a system, someone is developing a product, they used to develop it, and after the development is finished, after the prototyping is finished, and then it used to be tested. So this used to increase the cost a lot, and this also used to extend the timeline of the entire product development cycle by a huge margin. But the V cycle, how it works is it works hand in hand. So at every stage of development, there is a testing and validation uh, in parallel with it, which helps us reduce the number of errors and issues in the system before we actually build a prototype. Okay, so this is basically a brief overview of what MBD is. So the MBD process, if we go in a chronological order, the first part of an MBD process would be a requirement analysis. So let's say what is the requirement. So these requirements are developed by all the product development engineers working in any company uh, as to what they want to achieve out of the system. So let's say that somebody is developing a requirement for a auto unlock system in a car. So how that would work is, let's say that if you have the car key in your pocket, so you don't need to remove the key out of your pocket or press the unlock button. As soon as you move within the proximity of the vehicle, it would sense that the key is around and it would automatically unlock the driver door. So this is what the basic aim the product development engineers and the benchmarking engineers decide that they want out of the system. So based on this motive, requirements are generated. Requirements are generated by the feature owners. So this is what we term as feature owners in industry. So feature owners are basically drafting the requirements in a word format, and all these requirements contain each and every detail of how they want the system to be working, including the input parameters, output parameters, the CAN signals that are going to be involved, and the control logic that they want to incorporate in the ECU. So this is, and once the requirements are built, they are passed on to the model development engineers. So the process that we are talking about today. So in this model, uh, so what these model engineers do is they translate these requirements into a MATLAB Simulink model. So MATLAB Simulink is the most widely used tool to develop all this control logic and control software that would in turn eventually go into these ECU circuits. So these models are developed based on the requirements that they have got from the feature owners, and these are purely based on the mathematical mm, control logic that they have designed. So once these models have been built, so still we are not yet in a phase where we have an actual hardware on an actual circuit. Everything is still on the computer. So the model is still just built on the computer, but we can still simulate and we can still run and execute the model just like we would execute a software code and see if it works fine. So this is what we term as model in loop testing, where just basically a single model or many models connected to each other while integrated are being tested is called model in loop testing. We'll talk about model in loop, hardware in loop testing as we go ahead. So once these testing phases are completed and the model is built, this model is converted into a auto code. So in recent terms, what we term it as auto code generation. So this is also a facility provided in the MATLAB Simulink interface where the auto code is generated out of this model. So basically this models is just GUI based, what we would just plug and play on the screen. And based on these models, a code is generated, which is essentially a C code, a C programming code, a C language code. So these C code is what we call as an embedded C code. So this code is then integrated with a base software. So just talking in simpler terms, we have what an operating system on a computer. So even though we have an operating system on a computer, we need several applications to serve our purpose. We need a we need, like if we talk, we need a media player to play videos. We need a image viewer to view the images. We need a word editor to word edit word documents. So similarly, these models, when they are converted into software C code, we term as them as applications. And these applications are then integrated with what we call as a base software, which is generally an operating system of that ECU. So when they are successfully integrated, we get a flashable software. So flashing is a term which is a technical term of downloading and installing the software on the ECU. So ECU is basically a PCB consisting of a microcontroller and several other electronic components. So flashing is termed as installing that generated autocode integration software on the ECU. So yeah, this is the MBD cycle, what we were talking about earlier. So as the name suggests, it is literally in a V shape. That is why it is called a V cycle. So it all begins with system design and requirements modeling. So as we discussed, somebody comes up with a requirement, somebody comes up with what they want to get it out of the system, and that is translated into requirements, and those requirements are then translated into models, which we just discussed. So these models can also be called algorithms or just MATLAB models. So after these models are designed, they are tested in a just a computer environment. No hardware is still coming into picture. So this is what we call as mill testing. So if we go ahead, I'll quickly explain what all these testing phases mean. So just a particular model is developed for, let's say, one strategy, an ECU would have n number of strategies ranging from 100 to 500. So for all these 500 strategies, they would all have their own individual models. And all of these models are integrated to form one whole model package for a particular ECU. Let's say if we are talking about an engine control unit, So for engine control unit, there would be n number of strategies which would go into that model. And when all of these models are integrated, what we get is called a model package of that particular engine control unit. And that is tested just on a computer level, just on a model level. Within the MATLAB Simulink interface, it is known as model in loop testing. Software in loop testing is when after the code is generated, once the model is tested, it is converted into an embedded C code, and that code is tested with other parameters of the vehicle simulated. So we have still not yet come to a stage where we have actual hardware, actual ECUs, actual circuitries. Everything is still being done on a computer. So all of this code, once generated, or they are still simulated and run virtually to see if there are any errors found, if there are any discrepancies or inconsistencies within the system or within the coding, which can still be rectified before we actually release or publish a software which will be installed and flashed on a circuit. So once these two stages are done, we come to what is called a hardware in loop testing. So this hardware in loop testing is actually where we have the ECUs in hand. So all the ECUs that would eventually go in a vehicle, we all have all them in hand, and we actually flash them on the circuits with the help of what we call is CAN tools. So how the CAN protocol work on a vehicle, similarly we can simulate them even on our computers with the help of tools provided by Vector and certain number of companies. So based on these simulations, we can flash those or install those softwares on the ECUs, and we can test in an environment which is similar to a vehicle. So if we go ahead, this is what is a example of a hill system. So hardware in loop system, this is an example. This is just a reference image which I got off the internet. So the hill system basically has most of the components, actual original components that are going to be used in vehicles. And even in the product life cycle, some of the prototypes vehicles that are going to build, these are all the actual components that will go into that vehicle. So as you can see, this hill setup does not have all of the components that a vehicle has. Some of the components are absent, like the engine itself is not there, the HVAC case is not there. So all of these engine and everything are being simulated by this plant. So this is what we call as plant in technical terms in hill testing. And these plants just have a lot of code and simulation running on its back end, which simulates and which communicates with the rest of the system in such a way that it makes them believe that the engine and transmission and everything, all the other components which are absent, are actually present. So if you can see these harnesses going into the plant, these are actually the CAN harnesses and the electrical harnesses which are actually present on the vehicle. And all the communication taking place between the individual components and the plant is happening via CAN, like actually how it happens on a vehicle. So this is called as hardware in loop testing, where individual components are tested and individual ECUs are tested by their testing engineers. So now the entire process that we talk about, let's talk about it in an example form to better help understand what the actual process is. So let's take a basic example of a thermostat. So thermostat is what is used in all the ACs that we have in our homes, even in the AC and HVAC units that we have in our cars. So this is not essentially entirely accurate or entirely complex. This is just a simpler and very basic system that I can like make help understand everyone, make to help understand everyone. So let's say that we want to build a thermostat model. So thermostat is something that would control the temperature of a room or a vehicle. So some of the requirements that one would build based on this thermostat uh, is what is the desired temperature. Okay, so some of the requirements are what do you need in order for a thermostat to work. So even in the ACs that we have in our homes, we set the temperature. Let's say we want to keep it at 22, we want to keep it at 20, we want to keep it at 18. Even in our cars, we want to keep our temperature at high, low, or 25, 27. So these are all the desired temperature set by the user. So this is one of the requirement, one of the major point of requirement, that we need a parameter which would store the value of the input given by the user. Okay, so this is what the user wants. The user wants the temperature, let's say, of the room to be at 20 degrees Celsius. So, and there would also be a sensor in this system which would sense the actual temperature of the room. So this temperature sensor would be continuously sensing the temperature in the room uh, that is being achieved, and a control logic. So a control logic, basically how it works is uh, it is basically working on a mathematical equation. So for all the components, even for the HVAC or AC compressor control, even for engine control, or even for a transmission control unit, all of the control logic basically works on, when we break them down to its simplest form, they are purely mathematical equations that are converted into a control logic or into a flowchart, and those flowcharts are in turn converted into MATLAB models, what we just discussed. So we would not dive down deep into these control logics because they are basically part of control theory. But these control logics are what we model in the vehicle, and what we need is a output. So these are the requirements. Two inputs which are going into the system. One is the desired temperature which the user is setting. One is the current temperature which the sensor is sensing, and both of these inputs are going into the control logic, and this control logic is giving an output which in fact turns on and off the HVAC unit. So this is a basic requirement that we have derived based on our use case of a thermostat. So based on that, if we try to build a basic block diagram on a paper, this is how it would look like. So this is a set point that the user is setting. And so if we talk, this is a closed loop system. So how it would work is the sensor, the temperature that is being sensed in the room is being catched by the sensor, and sensor is actually transmitting that to the control logic again. So what the control logic is doing is it is actually sensing the difference between the current temperature and what is decided by the user. So let's say 20 degrees Celsius is what is desired by the user, but it's very hot outside and the actual temperature in the room is 30. So the controller is sensing that my current temperature and desired temperature delta is 8 degrees Celsius. So based on the control logic that is incorporated in the controller, it would command the HVAC unit to be turned on until the temperature of 20 is achieved in the room. And how it would know that temperature of 20 is achieved in the room? It would be with the help of this sensor. So once the temperature hits 30, the sensor would catch it. It would transmit it to the control logic. Control logic would know, okay, I've reached 30. It would stop the output and it would turn off the HVAC system. So once again it senses a delta between its desired temperature of 20, it will again turn on the HVAC system. This is how basically the ACs work. So now if we try to model this in MATLAB actually, I'll just show it in Paint, but this diagram is what would actually be there on just on paper. It would still need to be modeled. So if we show that in Paint, so I'll just like basically show what would happen actually in MATLAB. I don't have MATLAB license on this computer, so I'll just use Paint. So this is what we would use as a constant. We would term it as constant because it is being set by the user. This is the temperature that is being set by the user for the AC. This input is going into what we call as a add block. So blocks are basically an integral part of Simulink interface. So there are a variety of blocks that one can use to make a model or make a control logic based on their application and based on their use case. So this add block, as the name suggests, it just adds two inputs that it is receiving. So it has two inputs. It is basically just adding and subtracting one from another. So this would then go into a control logic. So just to describe or to indicate a control logic, I'm just including a block, but this block would have complex code integrated inside it. So when we try to access this block, it would then break down into further even more blocks, which would actually represent the entire control logic that we had designed on paper. So once, and the actual output of this system is the HVAC unit. So this is what we can call as HVAC. Okay, so this is what is an add block. Add block. So it is basically taking an input from the constant input from the constant block, which is basically given by the user. It is continuously sensing the temperature of the room, which is being supplied by the sensor. It is constantly trying to get a delta out of these two. So basically one is being subtracted from the other. This delta value is then being supplied to this control logic. This control logic basically works based on a mathematical equation. This control logic then, based on if the delta is zero, it works on either turning on or off the HVAC unit. So this is basically how a model would look like if you were to model it in MATLAB Simulink interface based on the requirements that we just drafted. So this is basically how the development process goes on in the industry, although it is a lot more complex, but this was just in simpler terms to help you all just get started and understand the concept. So these are some of the tools that are being used in the industry. So MATLAB Simulink is all the most widely used tool almost by all the industries. Some of the other tools which we have, Stateflow is also a part of the MATLAB Simulink interface, and Stateflow is basically the complex control logics, and Stateflow I would say is also very widely used in hand with MATLAB Simulink. GT Power is one another tool by a separate company which also serves the same purpose as MATLAB Simulink. And there are also custom tools, so custom softwares developed by companies. So let's say if we're talking about uh, Tata or Mahindra or any company. So these companies would also have their own custom tools which would model their which they would have built as per their requirement to model and develop their control units. So this was a brief overview. I'll also quickly show. This is actually very interesting. So this was the project which I did during my master's. So in this project, we made a control logic diagram. So the entire process which I just explained is included in this project. So in this project, we had basically modeled a automatic transmission control unit. So as in US, almost all the cars have automatic transmissions. So transmission control unit is something which is very important. So basically we made a MATLAB model, and we also made an engine model and a torque converter model and a wheel model. So wheel model is just in simpler terms, we have termed it as a wheel model, but it actually is a vehicle dynamics model which considers all the road loads, the wind loads, so basically all the dynamic equations of how a vehicle actually runs on the road. Okay, so if I show it to you, this is how the engine block is modeled. uh, this is all in very simpler terms. This is not how simple it would be on a vehicle. It would be 100 times more complex, but this is just a brief overview. Even I got started with these basic steps. So this is a basic control model of an engine. As we can see, we are getting a throttle as an input into this model. So basically what this throttle is our accelerated pedal. So the way we depress and press it, it gets converted into an actual numerical value or percentage of how much it wants the throttle to be open. And based on that, it is going as an input into this 2D table. So what this 2D table is basically it throttle versus engine speed diagram. So an engine speed is in RPM. So based on this throttle versus engine speed diagram, we have all these values of torque. So these type of diagrams one could expect from the engine manufacturer or the OEM. If themselves are manufacturing the engine team would have all this data because they have calibrated, they have dyno tested the engine, so they would know that at what throttle percentage and what engine speed uh, a particular amount of torque the engine would be giving as an output. So this 2D table, we basically this image that you see here just includes this entire 2D table. So what this control logic is doing is it is basically taking the throttle as an input. It is doing some amount of calculation. So this is basically a mathematical equation, an integral equation, which is just converted into a model. So this model then gives out an output of engine speed as well as the torque of the engine. Engine speed is just the direct output that we are getting from the y-axis of this table, but the torque output is actually what we are interested in. So just if you guys can make a note that from this model, the main output that we are interested in is the TE, the torque of the engine. So this is a perfect example of how we are talking about multiple models being integrated together and how one output of a particular model is being used as an input by some other model. So this was the engine model. An engine model is giving out as an output of TE. Now this TE output is being directly used by the torque converter model. So as you all would know, uh, in an automatic transmission vehicle, there would be no clutch, but there would be a torque converter. So basically, we also modeled this torque converter based on the equations that we were given. So this entire region that you see over here is just mathematical equations converted into the model. So now, as we can see, the NE, which was output of this engine model, is being used as an input in the torque converter model. And these 1D tables are basically some coefficients and ratios of the torque converter, which is basically design intent. It has nothing to do with the control logic. So the torque, based on the equations and based on the control logic that we have provided in this torque converter model, it is giving out an input. It is giving out two outputs, the torque of the turbine and the torque of the impeller, Ti and Tt. So after the engine model gave out two outputs, Ne and Te. Ne is being used by the torque converter model. Now we go ahead to the actual transmission model. So we this is the what we see on screen right now is actually a stick diagram which basically represents a six-speed automatic transmission. So this type of data is available with the transmission manufacturers or the team who is supplying the actual hardware or the actual physical transmission box gearbox to us. So this is basically all the ratios, gear ratios of the automatic transmission. So based on just these data that we have, we actually simulate first mathematically how the transmission works and how the actual shift takes place. So if I give a brief overview, how automatic transmission works is basically in our manual transmission vehicle, we change the gears by hand. So we basically decide that when we want our gears to be changed from 1 to 2 to 3 to 4. And it varies from person to person. Somebody likes changing their gears late, somebody wants to shift to second gear early. So all of this is basically varying from person to person in a manual transmission vehicle. Whereas in automatic transmission vehicle, this would all be taken care by a software which would sense the vehicle speed, which would sense the engine speed, which would sense the throttle input, which would sense the torque, which would sense the wheel friction, and decide when it wants to shift from 1 to 2, 2 to 3, or it wants to shift from 3 to 2. So these are basically a set of mathematical equations that I was talking about earlier, which represents the dynamics of these gears and these shifts from 1 to 2, 2 to 3, and so on. So these mathematical equations are hand calculated, and what we get in the end is basically these intermediate equations. So these equations are what actually we are going to script it in a form of code, and that code we are going to integrate in a MATLAB model, Simulink model, which would help us complete this entire model package. So based on this entire equation, uh, we would then be making a MATLAB model. So if I directly show the actual model, yeah. So this is the MATLAB script for shift logic. So all the equations we just saw, they would all need to be still coded in form of a MATLAB script, and that script is what we can see here. It is basically an if-else logic that we design. So this entire code is what we have incorporated in this block. So if you see this transmission block, it is basically a custom block. So MATLAB Simulink also has this feature of creating custom blocks. Let's say that you want to create any type of software, any type of code. You can make that code and you can create a block for it and you can save it for later use. So I can save this transmission block and I can use it at n number of places. So once we created this entire script, we basically integrated that into this block. This is the engine block that we just saw. So if you see in this global view, we are just seeing it as a simple block, the entire engine. But if we were to further expand it, it would look like this. It would look like this. So this basically, when we just collapse it, it gets broken down to the smaller view. So this is the engine block, this is the torque converter block that we discussed. So this is the transmission block. So the entire transmission block contains this script, and this is the wheels. So what we term as wheels is basically the vehicle dynamics calculations. So it has all the inputs like acceleration, the angular velocity, the angular output of the engines, and the road loads. So when I say road loads, means all the loads acting on the vehicle, the wind loads, the coefficient of friction on the wheels with the roads, and the actual uh, inertia of the vehicle. So all these loads are considered, and accordingly they are integrated into this wheel model, which is also a vehicle dynamics model. So how these individual models are integrated, this is the perfect example of that. And we are getting output as acceleration, angular velocity, and vehicle speed. So if we try to align what we just discussed earlier in the presentation with this concept, so this is what we would call as a completed model. So we still don't have any transmission with us. We still don't have any transmission control unit with us. Everything is entirely just on a computer. So after we model this, we can execute it. We can just play it like we would play a code, or we would run a software. So after we play it, we execute it, we actually get results in graph form. So as you can see, uh, it is not seen in this code, but in the transmission model, we have what we call them as scope. So these are called scope, like in basic term, what an oscilloscope is. It basically captures the graphs for us. It basically captures the signals. These signals are basically the outputs of all the ECUs. So these scopes are capturing all the signals, and they are basically showing them, displaying them in a graphical format. So if we see, these were the results that we got. These were the results that we got after we ran this simulation. And this is, so basically the entire dip in torque and even the shoot, this dip and this shoot is what represents the gear shift from first gear to second gear. This is what it represents. So this is what, like one would know that this system is entirely working fine. So if we see how it works is, this graph is basically representing the vehicle speed. So even in a manual transmission, if we are going in first gear, we were to upshift it in second gear, we would actually reduce the speed of the vehicle, and then we would shift it to second gear. So this graph basically represents that the speed was gradually increasing, then the shift from first to second gear took place. So the speed had a massive drop, and then it again started shooting back up. So this is how, based on the graphical interpretations, we can validate that the model is working fine. So the further stage is how they would look like it, although we didn't do that, but how they would look like is, once these models are validated and once these models are found to be working perfect, they would then be converted into a C code. That C code would be integrated with a base software, what we would call in simpler terms as an operating system. These integration of base, the model and the operating system would be called as a software package. That software package would be installed on the circuitry, and that circuitry would in turn control the actual transmission on a vehicle. So this was basically the entire model development process, just an introduction, but I hope that it will help you guys get started. And basically this process is, like I used some example of thermostat and transmission, but this is not just limited to that. Almost every logic present on the vehicle, almost everything that you do in a vehicle, even if you try to set your seats, even if you try to move your seats, when you're trying to press volume up, volume down button, when you're trying to press window up, window down button, when you're trying to press the button to release the trunk of the vehicle, when you are pressing the brake and the rear brake lights activate, everything, all of these things are taking place through the CAN communication, and these ECUs are everything is taking place to the ECUs, and all these ECUs are communicating with each other via CAN. So yeah, this was basic overview. Yeah, I will end my presentation here, and I'll be like taking questions if anyone wants it, or even if anyone has some questions at a later point of time, they can email it to me.
Hello, any question, guys?
No, sir.
No, sir.
No question. Okay. So I'll hand over the session to Sanjay sir, Head Automobile Engineering Department. Sanjay sir, it's over to you.
Yeah, thank you very much, Sandeep. I hope is it audible?
Yes, yeah,
Is it okay?
yeah,
Okay, thank you. Yeah, so first of all, it was very nice to see Harsh after a long time, right?
thank you,
संजय
sir.
सर एक
If
Yeah,
मिनट
I remember
संजय सर
correctly, me and Philips we are difficult.
संजय सर एक
Yeah,
मिनट एक मिनट हर्ष प्लीज switch on your camera so that
yes.
everyone can see your face.
oh yeah, yes,
Yeah, thank you. So, as I said, nice to see you after a long time, probably after
yes, sir,
3 4
likewise.
years, right? So,
Yes,
yeah, thank you. So, but I think it was uh, all the content covered was very. I mean, see, there are few untouched areas in academics which cannot be covered through curriculum. So, this kind of topics can be covered through webinars and seminars. So this was very, I think, nice. Like controller, like you talk about MATLAB and everything. So students obviously gain lot of things through this. So one thing is students of automobile or mechanical ADIT.
yes,
For you, this kind of opportunities are very rare. You should understand that your seniors are working worldwide at very good places, right? With big giants, big companies. So in future you can get any
hello.
Sir, your
Hello.
voice is breaking. Sanjay sir. कुलदीप संजय सर आवाज नहीं आ रहा.
एक सेकंड
I think some network issue.
Yeah, I think sorry for that. Due to some reason, this Wi-Fi got disconnected. Yeah, so on behalf of all the students, participants, and automobile engineering department, I would like to thank Mr. Harsh Acharya for delivering such a informative and very useful webinar. Right. So again, thanks to Kuldeep sir also, who has arranged this kind of webinar. It takes lots of efforts to arrange any kind of webinar or any kind of events, right? So Harsh, again, thank you very much from our side, and we would be happy to interact with you in future also. Fine.
Sure.
Thank you.
Yes, sure. No problem. Yeah, I'm glad to help. Yeah.
Thank you. So thank you to all. You may leave the session, and we will just end it again by thanking Harsh Acharya. Yeah, thank you all.
Thanks a lot, sir. Yeah, thanks a lot. Thanks, everyone.
Thank you.